Hi again, everybody. I thought I would start out with the example that sort of connected our concept of integral to our fundamental theorem. So we'll go back to our old friend, x squared dx, and instead of picking limits to be, 0 to 5 like we've done, or, 1 to 3 or anything like that, we're just going to generalize it. We're just going to go from a to b and kind of see what happens. Okay? So we'll take the integral of x squared from a to b, and we know that to be the limit as n goes to infinity, adding up all those rectangles from 1 to n, f of x sub I, delta x. And that's basically what we've done so far, up until Friday. So let's just try it out and see what happens. Our delta x, we can't get an exact number here, or just in terms of n, we have a b and an a to deal with. So b minus a over n, there's our delta x. Our x sub I is our starting location, which is a, plus delta x times I. So delta x is b minus a over n, and there's I of them. Okay? And f of x sub I, well, now we just got to substitute that into x squared. So that's going to be a plus b minus a over n I squared. And unfortunately, we really don't have much choice, but we're going to have to expand that out. A squared plus 2a b minus a over n i's, right? Just our routine, foiling, if you will. A squared plus 2b minus a over n I plus our last term squared. So b minus a squared over n squared I squared. And that takes care of f of x sub I and delta x. Now to put that whole thing together, our area is going to be our integral, for x squared is going to be back to the limit. And f of x sub I is that whole thing, 2a b minus a over n I plus b minus a squared over n squared I squared. That's just f of x sub I, right? So it's still times delta x, which is b minus a over n. Okay, so we're going to have to clean that up and see what happens. So now we really have no choice but to distribute our delta x over all the terms we got from our f of x sub I. So let's go ahead and take care of that. That's going to be a squared b minus a over n. A squared b minus a over n. Minus 2a b minus a quantity squared over n squared I plus b minus a cubed over n cubed I squared. Okay, and that's the result of just distributing this b minus a over all the terms in here. Okay, at this stage, I would hope we don't really need to separate them anymore. I think we've done enough of those where you can kind of see the sigma applies to this piece minus the sigma applying to this piece plus the sigma applying to that piece. Whether we add or subtract first or last doesn't really matter. You're still going to get the same kind of thing. So let's focus our attention on just the first part. Notice in the first part there's no i's. So I going from 1 to n doesn't change this number. It's still just a number. And you're going to add that number to itself and again and again and again n number of times. So this is like that other example we did where it was, negative 12 over n or 8 over n or whatever ones we did together. And you just add it n times. So a squared b minus a over n plus a squared b minus a over n, etc., n times. The n's are going to cancel. You have n number of times, and you're dividing by n each time. So that leaves you with just a squared b minus a. So the limit as n goes to infinity for, I'm sorry, we're not even applying the limit yet. Just the sigma part for a squared b minus a is just a squared b minus a. And if you need any refresher on, the whole trick with the n in the denominator like that, look back at our other examples and you'll see how it ends up canceling out. We're not quite as lucky over here. However, this is still just a number. This whole thing right here is just a number that you're multiplying by I. So if I is 1, it's this thing times 1, plus this thing times 2, plus this thing times 3. That thing is common to all of them. All of those terms have this in it. So I'm going to factor that out. Minus 2a b minus a squared over n squared. And what I'm left with is just I. But we have a formula for I when you're going from 1 to n. and that's n times n plus 1 over 2. I can do the same thing over here. I have b minus a cubed over n cubed, which is a common factor, n cubed, and I have just left the I squared. Now, the I squared for sigma was the, n times n plus 1 times 2n plus 1 over 6. And that takes care of the I squared. All right, it looks a little messy, so let's take a second here and take a look at what's happening as our limit goes from n to infinity. I think the first part you can tell there's no n involved, so that's just going to be a squared b minus a, no big deal. But over here, if you look carefully, this is n times n plus 1, so that's basically just n squared as the leading term. The plus n part that we would get doesn't have any effect on the limit as n goes to infinity. So all my eyes are doing is focusing on this part. Okay, this is the moment where we would normally do a little switcherooski, but I'm not even going to bother because we've seen it so many times you kind of see where this is going. The limit as n goes to infinity for n squared over n squared is 1. So all I'm left with 2a b minus a squared over 2. The 2's cancel. So this turns into a b minus a squared. Okay, again, the limit as n goes to infinity of just this part that has the n's is 1. The limit as n goes to infinity of just this part here, you've got an n cubed and a 2n cubed. I don't care about the other parts. As n goes to infinity, the only parts that are going to matter are those leading terms. So 2n cubed over n cubed goes to 2, which cancels out a little bit with the 6, leaving a 3. So I'm left with 1/3 b minus a cubed. Again, the limit as n goes to infinity. I'm just focusing in on the n's. If you multiply this all out and simplify it however you want to do it, you'll end up with a 2n cubed plus some other stuff over n cubed. So the limit as n goes to infinity for that would just be the 2, and I simplified that a little bit with the 6 that's already in the denominator. So this right here is actually the integral of x squared from a to b so far. Now, unfortunately, that's not very user-friendly. I don't really like the way this is, left because there's so many a's and b's that look like they can be simplified. So we're going to take a minute and actually simplify that. All right, so here is our sort of unsimplified version of, our integral for x squared from a to b. Let's go ahead and simplify that a little bit and see if we can't make this a little more user-friendly. Okay, so we've got a squared b minus a cubed minus a, this is going to be b squared minus 2ab plus a squared plus, I'll bring it down here for some room, 1/3 b minus a, b squared minus 2ab plus a squared. That's going to be a squared b minus a cubed minus ab squared plus 2a squared b minus a cubed plus, and here we go, 1/3, and now I'm going to do all this stuff. I'll do the b's first. So this is going to be b cubed minus 2ab squared plus a squared b. Now I'll do the a's, minus ab squared plus 2a squared b minus a cubed. And at this stage, hopefully you can see there's some things that sort of work themselves out. We have a, you know what, sorry about that, guys. I think I just accidentally copied over a minus instead of a plus. So bear with me for 1 second. Let me just double check. Yeah, these are pluses. I don't know. I think I just maybe miswrote it when I first copied it over. So this is plus, right? If you just look back at the original, all that's going to do, it's a very easy fix. Very easy fix. It's not really going to change much. And that brings this to a plus. They should all be plus. So once I get here, I have a squared b minus a cubed. That's fine. This is plus a times this whole thing. That's going to change this to plus ab squared plus, actually now that's going to actually be a minus 2ab. So we can fix that. And then plus a cubed. I kind of knew where this is supposed to be going, so as soon as I wrote this step, I had to pause it for a second and say, wait a second, I missed a sign. So let's go back here and just look. We've got a negative a cubed, now a plus a cubed, right? We have an a squared b minus 2a squared b. So that gives me a negative a squared b. I can't do anything with the ab squared yet, so that's just coming along for the ride. That's got to come along. And then now I've got in here, I've got some things I can simplify. I've got the 1/3 b cubed, nothing there, but I have negative 2ab squared and minus another ab squared. So that's negative 3ab squared plus a squared b plus 2a squared b. That's plus 3a squared b. And then minus a cubed along for the ride. The 1/3 kind of works a little bit here. I can take care of the 3's, but I can't do much about the b cubed and a cubed. So let's just go with that. We've got negative a squared b plus ab squared plus 1/3 b cubed minus ab squared plus a squared b minus 1/3 a cubed. I have a negative a squared b and a positive a squared b. I have a positive ab squared and a negative ab squared. So all I'm left with is b cubed over 3 minus a cubed over 3. And the connection we made in class, those of you that already turned to the dark side, realize that this was just the antiderivative of x squared. The antiderivative of x squared, if f prime is x squared, then you guys figured out that the original was x cubed over 3. Right? And then you put in the number 5 to get our, 0 to 5 trick. Well, this is the same thing, except it's in general. If x is 5, right, then b is 5. 5 cubed over 3, 5 cubed over 3 is 125 over 3, which is your 41 2/3. Oops. Let's try that again. 41 2/3, which is what we figured out from class. Minus the a cubed over 3, well, a was your starting point. If I'm starting at 0, well, I'm not really subtracting anything. This leads us to one of our first fundamental theorem components for our fundamental theorem of calculus, which I will show you in 2 seconds. All right, so suppose you have a function that you're trying to take the integral of from a to b. Well, the way to get it would be to take the antiderivative, and a lot of times we'll use a capital F to represent the antiderivative, evaluated at b minus the antiderivative evaluated at a. So we do upper minus lower. So f of b minus f of a, big F of b minus big F of a. This is your fundamental theorem of calculus. And depending on the book, I think in our book this is actually part 2, but it could be part 1. It doesn't really matter. It's just one component of your fundamental theorem of calculus. Okay? So again, if I were to do this from 0 to 5 for x squared, it would be as simple as just taking the antiderivative of the function evaluated at or from 0 to 5. So again, I would do upper limit minus lower limit. I know it seems silly to put it, but I'm just going to put the 0 anyway. And there's your 125 over 3. Okay? At this stage, usually people ask me, well, what about the plus c? Right? We're doing an antiderivative. Shouldn't there be a plus c? Well, if I do the plus c for this part and then subtract out the plus c from this part, it's the same plus c because we're starting with the same function. Those two c's would just cancel out. So there's no need for it. Okay? But this does lead us to a very important concept of how the area relates to our antiderivative. Some of you were trying to figure that out originally and just sort of did it and hope it worked out, but you didn't have a justification for it. Okay, this is the beginning of the justification. So this is part 1. Another part would be if you've got another function and you're going to call that function the integral from a to x, let's say, of f of t dt. Okay, so I'm generalizing another function as an integral. If I take the derivative of that function, I get right back to the original. So the derivative of the integral is the integrand. The integrand is, what you're starting with. Kind of like a radical and a radicand, right? The radicand is what's inside. The integrand is what's inside. So the integrand here is f of t dt. If I evaluate from a to x and take the derivative, I get just f of x. This is the next part for fundamental theorem of calculus. So these two things, these two relationships are the key to the next branch of calculus that we're going to study, integral calculus. Okay, I'm going to do a couple more videos with some examples of that and how it works, so hopefully that'll help with the actual homework, and we'll kind of go from there. Okay, let me know if you have any questions, and I will see you guys later.